Okay, so now that we've introduced the problem, we've set up our potential energy, we have the Hamiltonian that I've written out here already, and we need to solve this equation, h psi equals E psi, right? So we need to find what are the wave functions, the function psi, and the energies that satisfy this the Schrödinger equation for this system. Okay, so overall that's negative h bar squared over 2 times the reduced mass second derivative of the wave function with respect to x being the relative displacement between our two masses, plus 1/2 kx squared times psi is equal to E psi. Now, I glance at this, and this is not something that's obvious to me how to solve, and I don't expect you to be able to solve this. I do want you to understand like where this equation comes from, but in terms of solutions, somebody already did the work for us. So back in the 1800s, there were mathematicians that solved this problem just because it was interesting to them, not because there's any physical significance to it. And so there's, as part of the solutions, we get the wave functions and the energies. So we'll first look at the solutions that give us the energies. So the energies, we end up with a quantum number, just like with the particle in a box. There is integers involved in the solutions here. We give it unlike the particle in the box, we use a new letter to describe this. We use the letter V for vibration. So V can equal 0, 1, 2, ... And this comes from the solution. Just like we saw with the particle in a box, the integers sort of naturally arise from the way the solution happens. Same thing here. And so we end up with an energies for our different wave functions that depend on V. And the solution is that the energy is equal to h bar times the square root of k over mu times v plus 1/2. Okay, so these are quantized energies. We can only have specific energy levels with the quantum number v, and again, v starts at 0 and then increases. Now this is often rewritten. We take this square root of k over mu, and we define this as this variable omega, which is equal to square root of k over mu. And so this shows that there's a relationship in the energy levels between the strength of the bond and the reduced mass. Those both matter inversely, right? So increase in the so if we increase the force constant k, that will lead to a higher value of omega, and if so, increase k, increase omega. Whereas if we increase mu, that actually leads to a lower value of omega since it's in the denominator. Okay, and so this is often written as h bar omega times v plus 1/2. And there's actually, there's actually a way to rewrite this in slightly different units too. We often write nu, and this is very confusing because nu and v look very similar, but they're not the same. So this is the Greek letter nu, not our quantum number. If we define this as 1 over 2 pi square root of k over mu, this gives us the frequency in hertz, whereas omega has this factor of 2 pi that's present. And so we can also rewrite this as E, as depending on v, is h nu times v plus 1/2. And I'll again emphasize this is a nu, this is a v. And I'll try and make sure to always have this curl on the nu to make it obvious. Now, what do these look like? So what we see is we have energy levels that depend on this frequency here, h nu, and we get spacing between them of v. Each v level is h nu apart. So if we kind of take our harmonic potential here and kind of map this onto it, we'll get equally spaced energy levels. So this is sort of representing the energies here. And this is v equals 0, v equals 1, v equals 2, on up. So for v equals 0, we get 1/2 h nu, and then we get 3/2 h nu for v equals 1, 5/2 h nu for v equals 2, and you just add an h nu for each energy level. And so this is directly related to the frequency of the oscillation. So I skipped over this a little bit, but this is in your textbook. It goes over this new here. This is the frequency of the oscillation of our harmonic oscillator. So this is how many times does it go back and forth? Does it stretch back and forth in a second, right? So nu is in units of hertz. Now in quantum mechanics, or I should say in spectroscopy, we often rewrite this in terms of wave numbers. So we'll look at yet another version of this in just a little bit. But one last thing I want to point out is the fact that even when we have a value of v equals 0, even when we're at the lowest possible energy level, the energy does not equal 0. And so there's always this energy of 1/2 h nu that's present, right? So even at this lowest energy level here, let's use a different color, right? So this is what's known as 0 point energy. And there's no way to get this out of the system. The molecule is always vibrating a little bit, even when it's at its lowest energy state, and we can't get rid of that vibration. So this is one of the interesting things about quantum mechanics, is this idea that our system can't ever truly be at rest. There's always some amount of vibration that's happening, some amount of energy in the system, but we can't actually use that energy for anything. It's just sort of stuck there, right? And there's all sorts of like new age pseudoscience stuff that says, oh, we can use the 0 point energy of the universe to solve all the problems of the world and make you rich and famous and beautiful and whatever else. And that is completely bogus. The idea of 0 point energy is scientifically true, but we can't actually use it for anything.